This is the Turf Zone Podcast, your central information and news hub, bringing together professionals from turf associations across multiple states to share things to help you in your business. Brought to you in partnership with our friends at the Pennsylvania Turfgrass Council. Now, let's get in the zone.
Welcome to the Turf Zone. In this episode of Pennsylvania Turfgrass, we feature an article from Max Schlossberg, Ph.D., and Nate Leiby, MS graduate student at the Center for Turfgrass Science at Penn State University. The article is titled, How Does Fertilizer N Evade Turfgrass Assimilation as Gas? Well, to the satisfaction of article browsers, more easily and often than most realize. But the best answer remains, it depends. Turfgrass requires greater quantities of N than any other mineral nutrient, and N sufficiency is promptly supported, or N deficiency is promptly reversed, by application of soluble N fertilizers containing urea, NH4, and or NO3. There are four N-rich gases that arise from N fertilizers: dinitrogen, or N2, nitrous oxide, N2O, nitric oxide, NO, and ammonia, NH3. In fact, every plant available N form, urea, NO3, and NH4, or intermediate, NO2, serves as soil feedstock for at least one of the above gases. Evolution of these gases from originally plant available N forms is undesirable. But once emitted, N2 is the least problematic of the bunch. N2O emissions. Agricultural soil is the greatest source of anthropogenic N2O emission on Earth, accounting for nearly 70% of annual totals. Industry and combustion, fossil and other fuels, are the next greatest contributors. Nitrous oxide is a tenacious greenhouse gas that produces protective ozone and claims very few opportunities for transformation or sequestration. Incomplete soil denitrification of nitrate. Denitrification is the microbiologically mediated reduction of NO2 and or NO3 following incorporation of soluble N fertilizer into warm, saturated soil. Under such conditions, the nitrate fraction of a soluble fertilizer application relates directly to early denitrification severity. Turfgrass systems maintained on highly porous root zones underlain by functional drainage are unlikely to lose N via denitrification, while systems maintained on native soils having high organic matter content and or water retention are more likely, especially in mid to late summer. This is the part of the article where we considered introducing complete versus incomplete denitrification and describing the more benign product, N2, of the former and all of the abiotic factors identified by research as comparative facilitators of it. But in the context of modern cultural techniques developed and or adopted by the most effective turfgrass managers worldwide, it's a non-starter. No turfgrass manager should maximize water-filled pore space in efforts toward favoring the N2 denitrification product. Incomplete soil nitrification of ammonium. Nitrification is the microbiologically mediated oxidation of soil ammonium, or NH4, and a notoriously prolific generator of soil acidity. Nitrification is a two-stage process, each depending on a separate genus of chemolithotrophic microbes. Regrettably, the second stage, oxidation of NO2 to NO3, is often limited by success of the first, oxidation of NH4 to NO2. Regrettably, the second stage, oxidation of NO2 to NO3, is often limited by success of the first, oxidation of NH4 to NO2, which constitutes feedback inhibition, but by no means incites greater risk to the product of the first stage, right? Wrong. Local oxygen depletion incites electron acceptance by the freshly oxidized NO2, catastrophically reducing it to NO or N2O. Most readers will recognize fate, it seems, is not without any sense of irony, as a quote by Morpheus in The Matrix. But how many know Morpheus was referring to nitrogen? NH3 emissions. Most atmospheric ammonia in North America originates from livestock operations and fertilizer application. In the presence of nitrate or sulfate, NH3 constitutes the most significant and influential precursor to smog formation, i.e., particulate matter, less than 2.5 micrometers in diameter, or PM2.5. Elevated PM2.5 levels are monitored in numerous non-attainment regions along the U.S. eastern seaboard and are statistically correlated to adverse health effects. Furthermore, ammonia deposition to surfaces, the primary atmospheric removal mechanism, is considered a significant threat to terrestrial and aquatic ecosystem health. Urea hydrolysis. Of the soluble N fertilizers, urea is the safest, lowest risk of desiccating tissue, and most cost-effective on a unit N basis. Current urea fertilizer best management practices, or BMPs, encourage prompt soil incorporation by cultivation, coinciding rainfall, or scheduled irrigation events. Yet turfgrass managers' short-term prioritization of nutrient sufficiency and clientele satisfaction can preclude rainfall or irrigation concomitants. A sizable body of published results, old and new, confirm the cost of such inaction. Most recently, following granular urea N application to a K bluegrass lawn at 0.9 pounds of nitrogen per 1,000 square feet, Penn State University researchers determined 23% of the applied urea N volatilized over just 3 days of dry conditions. Regarding foliar application of urea N at 0.15 to 0.41 pounds of nitrogen per 1,000 square feet to putting greens, Penn State University researchers directly measured gaseous NH3 loss of 5 to 11% of the applied fertilizer over 24 hours of dry conditions. Disassociation of ammonium. Ammonium, or NH4, fertilizer, as well as NH4, either hydrolyzed from urea fertilizer or mineralized from organic matter, comprise a plant available N form. However, soil NH4 is subject to gaseous loss. Conditions favoring this fate include limited oxygen that incites incomplete denitrification to NO or N2O emission, as described, and moderate to severe alkalinity causing NH4 to donate its proton and volatilize as NH3. Soluble NH4 sulfate fertilizer is the N source of choice to supply both plant available N and pH lowering acid. However, turfgrass soils and root zones with pH levels greater than 7.9 are actually too alkaline to support both objectives. Spoiler alert, plant available N delivery will fall short of the application rate. Severely alkaline soil is better acidified and end fertilized by application of NH4 thiosulfate or combinations of 2100 and flowable elemental sulfur or K-thiosulfate, all complemented by nitrification inhibitors. Preventing gaseous loss of fertilizer N. Employ physical cultivation to maximize air-filled pore space in the upper root zone and adopt a frugal and unenthusiastic irrigation ideology. These efforts will support gas exchange and an aerobic rhizosphere more effectively than the alternative. Avoid NO3 N sources when fertilizing. Area under establishment, poorly drained areas at the onset of a wet season, or prolonged or intense precipitation event and in the warmest months of the growing season. Avoid conventional urea N sources when rainfall or irrigation is unavailable, temperatures are in excess of 85 degrees Fahrenheit, treatment areas are moderately to severely alkaline, excessively thatchy, and or within a PM 2.5 non-attainment region. Instead, apply N fertilizers that feature efficiency enhancements in accordance with regulations and as needed to support desired density and vigor. Field research described above shows supplanting 25% of conventional urea N with polymer sulfur-coated urea prevented 6.5% of the fertilizer N from volatilizing 0 to 3 days following broadcast application. When rainfall or irrigation is unavailable, yet fully soluble N is needed by a system growing on acidic to neutral soil, apply NH4, urea, and or urea formaldehyde reaction product-based N sources, complemented by 0.1% N-butyl thiophosphoric triamide, and 2.0% dicyandiamide, urease, and nitrification inhibitors, respectively. Above described research showed over the 3 days following application of 0.9 pounds of nitrogen per 1,000 square feet of Kentucky bluegrass, granular enhanced deficiency urea, stabilized with NBPT and DCD, emitted less than half the NH3 as conventional urea. Reapply in accordance with regulations and only as needed to support desired density and vigor. Future direction and summary. Ongoing field research comprising the co-author's graduate thesis is evaluating NH3 volatilization and associated factors following urea and urea-based fertilizer application to creeping bentgrass fairways and putting greens. The more interesting of the experimental treatments is the complementing of foliar urea N applications by a petroleum-derived spray oil. More results are pending. To date, our research fully supports the 2014 designation of NBPT amendment of urea as a Category 1 strategy or technique for abatement of NH3 emissions by the UNECE Task Force on Reactive Nitrogen. Category 1 techniques are deemed practical, verifiably efficient, and recommended for use in abatement strategies relative to a broadcast application of conventional urea fertilizer. If no other soluble N fertilizer source is available to support a critically important granular application under warm, dry conditions, then employ of a NBPT plus DCD amended urea fertilizer constitutes a recommended best management practice. For all charts, photos, and resources associated with this article, check out our show notes. And don't miss an episode of Pennsylvania Turfgrass. Subscribe at Apple Podcasts, Spotify, or wherever you get your podcasts. You can also check us out at theturfzone.com.
You've been listening to The Turf Zone. For more episodes of The Turf Zone, visit theturfzone.com and subscribe on Apple Podcasts, Stitcher, or your favorite podcast app.